Okay, welcome everyone. Today we will continue our discussion on support vector machines. We start with the binary classification problem. So we have a data set of the form x1, y1 up to xn, yn, where the labels are binary valued. So each yi is -1 or +1, and the data set is linearly separable. We are interested in a decision rule of the form y equals sine of w transpose x plus b. W is the weight vector and b is the bias term. And we want to select w and b to maximize the margin of classification. In the last lecture, we formulated this as a quadratic optimization problem. So we showed that we can find the following solution. We can find the solution to the following optimization. We minimize this quantity such that yn w transpose xn plus b is greater than or equal to 1 for all n in the set 1 to capital N. Okay, so this was the problem that we would like to solve over with respect to W and B, and the solution for this problem will lead us to the support vector machine, which not only perfectly separates our data set but finds the decision boundary with the maximum classification margin. Now what we will do today's lecture, first we will propose a dual formulation. Then we will identify support vectors for our solution. And third and most importantly, we will show how we can extend this to nonlinear transformations. Okay, so we'll start with the dual formulation. So our original formulation is what is called the primal formulation of SVM. Here our variables are W and B, the weight vector and the bias term. Our objective is to minimize the following term, half W transpose W, and our constraints where we had one constraint for each training point. Okay. What we want to first do is, so this is a constraint optimization because we have explicit constraints. We have n constraints, one for each training point. Our first step is to transform this into an unconstrained optimization. by introducing some additional variables, and then this will lead us to the dual formulation. To transform a constraint optimization problem into an unconstrained one, we use what is called a Lagrangian function. So the Lagrangian is a function of the weight and bias, and it also has some new variables which we'll denote by alpha. And it is obtained by taking the objective function, which was half W transpose W, and subtracting a contribution from each of the constraints. So the constraint we had was Yn W transpose Xn plus Ynb. This was the constraint. We subtract 1 from it because we had the constraint was Yn W transpose Xn plus Yn b minus 1. So we bring this one to the left hand side, and this is how we get this constraint up here. And then we multiply it by a quantity, a variable called alpha n, and we sum this from n equals 1 to capital N. So we have one term for each of the constraints in the optimization problem, and then we multiply it by the corresponding Lagrange. These variables here are called the dual variables. And so now this expression is known as the Lagrangian function. Okay? Alpha 1, alpha 2 up to alpha n are dual variables. So it turns out that the optimal solution of the constraint optimization problem can be also obtained using the Lagrangian function, where we still minimize over the variables w and b, and we maximize over the variable alpha, such that all the alpha i's are non-negative. So in other words, we can do the maximization with respect to alpha such that all the alpha i's are positive. We can minimize over the variables w and b L of w, b, and alpha. So in a sense, this is an unconstrained optimization problem, essentially, except for the fact that the alpha i's are positive, but that is, there are easy ways to handle this simple constraint. So this is essentially an unconstrained optimization. We have introduced a set of new variables called the dual variables. We have added a penalty term, if you will, for each constraint. And now we get a new function which can be, which we can use to solve essentially an unconstrained optimization problem involving this new dual variables alpha and the original variables w and p. So the good thing is when we have a problem like this, we can try to solve it using standard techniques. So let's consider first the inner minimization. We want to minimize with respect to w and b L of w, b, and alpha. So we will then do the outer maximization. First we will do the inner minimization. The good news here is that there are no constraints with respect to w and b. So this becomes a completely unconstrained problem, and we can take the gradient with respect to w of L of w, b, and alpha and set it to 0. Take the derivative with respect to b because b is a scalar, set it to 0 and try to simplify. So let's look at the first term. Since if you recall, L of W, B and alpha is half W transpose W minus n equals 1 to capital N alpha n yn W transpose xn plus yn b minus 1. It turns out that the gradient is easy to compute with respect to W. It's the gradient of the first term, which is W, minus, again, the gradient of the second term is easy to compute. It's just this, alpha times yn xn, and this we want to set to 0. So this means that W, the optimal solution, can be written in this form, alpha n yn xn. So if we have the solution for the dual variables, we can then express the optimal W in terms of a linear sum involving alpha n, yn and xn. Similarly, if we set the partial derivatives to 0, then what we get is, if we take the derivative of the Lagrangian function and set it to 0, you can see that there's only one term that depends on b, and that would imply that simply the summation of n going from 1 to n, alpha n, yn equals 0. So now we can use these two conditions to simplify the Lagrangian. We can use star and the double star, these two conditions, to simplify the Lagrangian. So remember our expression for the Lagrangian. This is half W transpose W minus summation of n going from 1 to n alpha n yn W transpose xn plus yn b minus 1. And so we can write it as half W transpose W minus summation of n going from 1 to n alpha n yn W transpose xn minus summation of n going from 1 to n alpha n yn b plus summation of n going from 1 to n alpha n. Okay. Now the point here is that let's look at the second and the third term. The first term is as it is. For the second term, I will take W outside because it does not depend on n, and I will write the summation of n going from 1 to n alpha n yn xn. For the third term, I will take b outside. It's a constant not depending on n, and alpha n yn. And the last term is n going from 1 to n alpha n. We just showed from the previous page that this quantity here equals W and this quantity is 0. So if you substitute the two, what you get is minus half W transpose W plus the summation of n going from 1 to n alpha n. And so if we substitute for W, since W is equal to the quantity here, and we do a little bit of simplification, this will be summation of n going from 1 to n alpha n minus half times summation of n going from 1 to n summation of m going from 1 to n alpha m ym xn transpose xm. So this is our new, this is what we get for the simplified expression for the Lagrangian after we solve the inner minimization. So we'll call this L of alpha. So now to get the optimal solution, we want to maximize L of alpha, where alpha are the dual variables. So subject to the fact that each alpha I is positive, as well as we have to account for any constraints we got when we did the inner minimization. If we go back and see what constraints we had, the first we had a star and double star. We had two conditions. Now the first one was not really a constraint. It tells us how to compute W from the alpha n's. But the second condition is a clear constraint because we are taking the sum of alpha n yn and setting to 0. So we have to put this and we have to now add this constraint. So it turns out that this is also a quadratic program. Okay. We can write L of alpha, which is this quantity in the form P transpose alpha minus half alpha transpose the matrix M times alpha, where P is the all one vector, which is how we get the summation over alpha n's. And M is the matrix of the form y1 times y1, x1 transpose x1, y1, y2, x1 transpose x2, up to y1, yn, x1 transpose xn, y2, y1, x2 transpose x1, y2, y2, x2 transpose x2, y2, yn, x2 transpose xn, all the way up to yn, y1, xn transpose x1, up to yn, yn, xn transpose xn. So this is a quadratic program where now we have identified what the P and M terms are. Our constraint, we have one linear constraint, it's of the form y transpose alpha equals 0, and our bounds in the quadratic program are that alpha i's are between 0 and infinity, where I goes from 1 to n. So the point is that this problem can also be solved using a quadratic programming solver. Just like the original primal problem could be solved using a quadratic programming solver, the outer maximization can also be solved. However, we have eliminated the variables w and d. We are no longer optimizing over it. And this particular problem is known as the dual formulation. So again, the dual optimization problem involves, instead we can maximize half alpha transpose m alpha minus p transpose alpha, subject to maximize over the variables alpha, subject to the constraint that y transpose alpha equals 0 and that all our variables are between 0 and infinity. So if we find if alpha star is a solution to this problem, then we can find the weight vector w, which is n equals 1 to n alpha n star yn xn. So this is what the duality theory in optimization tells us, that we can transform the original optimization problem into an alternative form called the dual problem. And once we solve the dual problem, which in this case can also be done using a quadratic program, we can then find the optimal W using this particular relation. There is one more thing that is associated with this method, and that is called the KKT condition for optimization. And it essentially says that in addition, the primal and dual variables must satisfy the following solution. So the primal variables the primal variables are w and b. The dual variables is alpha, and they must satisfy the following condition. We look at, so this was the constraint we had to satisfy in the brackets. Alpha n was the penalty term associated with the violation of this constraint, and this must be 0. This is what the KKT condition says, that for the optimal solution, the dual and primal variables must satisfy this constraint. And what this is saying is that either alpha n is 0, or if alpha n is not equal to 0, then we must have that W transpose xn plus b must equal, or yn times that, there's a yn I was missing here, this must equal 1. So in other words, if alpha n is not equal to 0 for a given point, then this condition must be satisfied with equality. So if alpha n is not equal to 0, then yn W transpose xn plus b must equal 1, that is xn and yn is a point on the Xn and Yn is a point that satisfies the constraint with equality. Such a point is called a support vector. Why do we call it a support vector? Well, what it means is that algebraically, removing any point that is not a support vector will not change the decision boundary. And geometrically, the support vector is a closest point to the decision boundary. Let's understand this through a figure. So imagine that we have some points like this, and we find that the solution gives us this is a solution of our decision of the optimization problem for SVM. Then if we look at the points that are closest to the decision boundary, perhaps these 2 points are on one side and this point is on the other side. So imagine that there are 3 points, this one, and this one. These are what are called the support vectors. These are the only points at which alpha i's will be non-zero. For all the remaining points, the dual variables will be zero. So the dual variables will immediately tell us which points are the support vectors and which are not. Removing any of these points, so if we had removed this point, for example, we would not change our optimization problem. We will still get this to be the decision boundary, and we will still get that the classification margin and so on is dictated by these 3 points. So removing any point that is not a support vector will not change the optimal solution. And it is only for the points that are the support vectors that the dual variables are non-zero, and these points are always the closest points to the decision boundary, meaning that they constitute the margin of our classification. So thus the dual variable immediately tells us which points are the support vectors. Now this is the first part of today's lecture. Uh, Note that once we have the final thing is once we have support vectors, the solution W star, the optimal weight vector, is given by the summation of alpha n, yn, xn. But since alpha n's are only non-zeros for the support vectors, we can write this as summation over all points xn, that is a support vector of alpha n, yn, xn. And then b can be obtained by selecting any xn, yn that is a support vector such that Yn W transpose Xn plus B equals 1. So this completes the dual formulation of support vector machines.